we're going to talk about how to graph a rational function. There are several things to consider when graphing rational functions. For example, because we will have a function in the denominator, we need to be careful to avoid values that make the denominator 0. Having some values that may make the denominator 0 restricts the domain. In general, there is a process we should follow that will make it easier to graph rational functions. First, we should determine the domain. We need to find out if there are any values of x for which the function is undefined. We do this by setting the denominator equal to 0 and solving for x. This will let us know if there are any vertical asymptotes we should look for. Next, we'll want to find the x and y intercepts. This will give us points to graph, or will determine that all or part of the graph does not intersect either axis. Then we'll calculate the limits of the function. We'll want to calculate the limit as x approaches infinity, as well as the limit when x approaches negative infinity. This will determine the end behavior of the graph and whether or not it approaches certain values of y as x increases or decreases. In other words, taking the limit will determine any horizontal asymptotes of the function. The next step is to find the vertical asymptotes. Recall that we touched on this in step 1, when we found the zeros of the denominator. In this step, we'll test those values by taking the limit as x approaches them from both the left and right, and determine if they are asymptotes of the graph. Finally, we will calculate the first and second derivatives of the rational function. By calculating the first derivative, we will be able to find the critical values of the function, which tells us where the function is increasing or decreasing. We will also be able to determine the extrema of the function if any exist. The second derivative will help us find the intervals where the function is concave up or concave down and where the inflection points lie. In this problem, we are going to graph this rational function. So we have f of x equals 7 plus x over x squared minus 16. Our first step will be to determine the domain of the function. To do this, we need to find the zeros of the denominator by setting that denominator equal to 0 and solving for x. We have x squared minus 16 equals 0. By adding 16 to both sides to isolate the variable term, then taking the square root of each side, we can see that the function is defined for all values except positive and negative 4. So we know that these two values will be ones we'll want to test later to determine if they are vertical asymptotes. Next, we want to find the x and y intercepts. We'll start with the y-intercepts, which occur when x equals 0. So we'll substitute 0 into the equation for x and solve. Simplifying, we now have f of 0 equals negative 7/16. So the graph crosses the y-axis at negative 7/16, which is close to negative 1/2. Next, let's find the x-intercepts. Set the entire equation equal to 0 and solve for x. Multiply both sides of the equation by x squared minus 16 to get 0 equals 7 plus x. Subtracting 7 from both sides, we have an x-intercept of negative 7. Now that we have our x and y intercepts, we can evaluate the limits of f of x and determine the end behavior of the graph. Finding the limit as x approaches infinity or negative infinity, we find that the limits are both equal to 0. Therefore, we know there is a horizontal asymptote at y equals 0. Our next step is to determine whether or not f has any vertical asymptotes. We already found the zeros of the function in step 1. They were positive and negative 4. Now we want to test those values to see if they are vertical asymptotes. We'll do this by taking the one-sided limit of the function using each value. To find the limit as x approaches a value from the left, try test points that lie to the left of the value. To find the limit as x approaches a value from the right, try test points that lie to the right of the value. For negative 4, this gives us the limit as x approaches negative 4 from the left equals infinity, and the limit as x approaches negative 4 from the right equals negative infinity. For positive 4, this gives us the limit as x approaches 4 from the left equals negative infinity, and the limit as x approaches 4 from the right equals infinity. Again, since the limits are not equal, we know this is an asymptote of the function. Now we'll calculate the first derivative. This gives us f prime of x equals 1 times the quantity x squared minus 16 minus 2x times the quantity 7 plus x all over the quantity x squared minus 16 squared. After simplifying, we have negative x squared minus 14x minus 16 over the quantity x squared minus 16 all squared. Notice that the numerator is a polynomial that we can't easily factor. Using the quadratic formula, we get that x equals approximately negative 12.75 and negative 1.26. These values are the critical values since these are the values where the derivative equals 0. We already know that the function is undefined when x equals negative 4 or 4. However, these values are not in the domain of the function. To determine where f is increasing and decreasing, we'll need to break up the interval negative infinity to infinity into smaller intervals. Let's break the interval into 4 smaller intervals. Now we have the intervals from negative infinity to negative 4 to 0, 0 to 4, and 4 to positive infinity to work with. We need to choose values for x to determine where f is increasing or decreasing. We'll use the points x equals negative 5, x equals negative 2, x equals 2, and x equals 5 as our test points from each interval. Starting with x equals negative 5, if we plug negative 5 into the derivative and evaluate it, we'll get a positive number in the numerator and a positive number in the denominator. What this means is that f is increasing on the interval from negative infinity to negative 4. Next, we'll look at the interval from negative 4 to 0. If we plug negative 2 into the derivative, we'll get positive values in both the numerator and denominator. As we saw with the previous interval, this means that f is increasing on the interval negative 4 to 0. In the next interval, we'll use x equals 2 and find that the numerator is negative, but the denominator is positive. This means the value of f prime at 2 is negative, which means f is decreasing over the interval 0 to 4. Finally, we'll test x equals 5. Just like the previous interval, we can see that f prime is negative at this value, and therefore f is decreasing on the interval 4 to infinity. We've now come to the last step before graphing, which is to take the second derivative to determine where x is concave up and concave down. If we take the second derivative, we get this equation, which is f double prime of x is equal to 2x cubed plus 42x squared plus 96x plus 224 all over the quantity x squared minus 16 cubed. To do this, we need to find the zeros of the numerator and find where f double prime is undefined. If we try to do this, we find that the numerator does not have any real roots. In addition, f double prime is never undefined in the domain of f because we do not include the values of negative 4 and 4 in the domain. In this case, to determine concavity, we would need to break up the interval negative infinity to infinity and test points, just like we did with the first derivative. In doing this, we'd find that f is concave up from negative infinity to negative 4, concave down from negative 4 to 4, and concave up from 4 to infinity. Now, let's graph the equation. Now we'll graph the original equation. We can use the information we found previously to help us do this. If we look at the table, we know we have two vertical asymptotes at x equals negative 4 and x equals 4, so we'll plot these on the graph. Notice that the lines are dashed because the graph does not contain these values. We also know we have a horizontal asymptote at y equals 0, so we can plot this on the graph as well. Now let's plot our intercepts. We have one at negative 7, 0, and another at negative 7 over 16, 0. So we know one branch of the graph is going to cross the x-axis at negative 7. We also know that this branch is concave up and that it approaches the line x equals -4, so let's graph this branch. The critical value on this branch is at approximately -12.75, -0.04. Now let's graph the second branch. This branch is concave down on the interval from -4 to 4 and crosses the y-axis at -7/16. The second critical value is on this branch at approximately -1.26, -0.4. Let's graph the third branch. We know this branch does not cross the x-axis, but it does approach both asymptotes. So we draw something like this for the third branch. Now we have the full graph of the function f of x equals 7 plus x over x squared minus 16. Notice that f changes concavity at -4 and 4. However, there are no critical values at these points because f is not continuous at x equals -4 or x equals 4.